Alright, hello class. Okay, so we're going to talk about the energy of a system. And, we have to be clear what a system is. There's different ways you can define a system. And in the problem we did before, we found the potential energy function. And we considered Q1 to be fixed and Q2 could, move around. And, it moved from some point and ended up at another point, but Q1 was fixed. And so there's kind of different ways we can define our system. In that case, what we did, it would make sense to say our system was Q2. So that's our system, and Q1 is external. So we had our system, which was being acted on by an external force. And so this object, Q2, had a potential energy that depended on where it was relative to the source of that force acting on it. But another way we could define this is we could say that our system is Q1 plus Q2. And in that case, the energy that we would calculate would be the energy of the system. It's shared among these two particles. Like, let's say before we said Q1 is fixed. And so in that case, it makes sense to consider our system to just be Q2 if Q1 is fixed. Like, from an analogy for mechanics, say we have the Earth, and say we have a mass, and we drop this mass and it falls down and hits the Earth. We consider our system just to be the mass and the Earth to be something external. Another way to look at it would be say that the system was the mass and the Earth, and this potential energy, U equals mgh, that's energy that's shared by the system. It doesn't belong to one part of it. And so if we release this mass, what's going to happen is it's going to fall down to the Earth. Also, the Earth is going to rise up to meet the mass. That's what happens in reality. Now, the Earth happens to be a lot bigger than the mass. And so the amount that the Earth moves is completely, impossible to even detect. But, technically it should exist. There's a gravitational force between these two objects. There is a force on the Earth. And so it should accelerate upwards. Now, but again, the Earth is big enough it can be considered fixed. And so if you have like one fixed object and another moving object, like we did in the last video, then it makes sense to define your system to just be the particle that can move. But more generally, let's say that, we brought Q2 over here, and so now these objects are right here at this location. And what if we release them both? So like say we were holding Q1 down when Q2 was brought into this position where they're separated by a distance r. Now we call our system to be both of these particles, and this potential energy function would represent the energy of the system. And if we release these masses, say these are positive charges, they're going to move apart from each other. And so that potential energy that's a property of the system, that's going to be converted into kinetic energy that can go into either particle. And so, we should be clear by what we're talking about when we mean a system of particles. And generally, energy, is shared between all of the particles. So a lot of times, though, we just consider it a special case where one object is fixed. But now we want to consider this as a system where everything is free to move. And so the energy, in this case, we already calculated that. We're just kind of interpreting it a little differently now. Because we freed Q1, so now it is free to move. But what if we had 3 or 4 or 5 particles? How much energy would there be in that case? So I'm going to just draw 3 particles. Now, we have these 3 particles here. That's our system. And I want to know how much potential energy is stored in this configuration. Like, say these are all positive charges. So they're all pushing apart from each other. And so if there's nothing holding them back, if we place them here and then just let them go, they're at rest now, but because of these forces, they're all going to move away and they're going to acquire kinetic energy. So there's energy stored in the system, and I want to know how much energy is stored in this system. Now, we're going to find these distances, like the distance between Q1 and Q2. Let's call that R12. This one would be R13, and here R23. So I know the total amount of energy in the system. Now, it's very important to understand that the energy stored in the system only depends on the configuration of the system. It does not depend on history at all. Like, how did these particles get to these locations? We don't care. The energy is just a property of the forces involved and just the geometry, like the distances involved. So it doesn't matter how you got these particles here. And then allows us to calculate this, the energy of the configuration, where we can imagine that all these charges were all very far away from where they're eventually going to end up. They're so far away that they're not interacting with each other at all. And then let's imagine building up this configuration one charge at a time. So, again, there's no charges here on the board. We're not going to erase the picture. But just imagine there are no charges. They're all very far away. And I'm going to bring Q1 in from very far away and place it here. How much energy did that take? And the answer is, let's call that U1. That's 0. Doesn't take any energy. Why doesn't it take energy to bring Q1 from infinitely far away to here? Because there's no forces acting on it. Charge 2 and 3 are still far away. So you can imagine if this is out in the middle of like the galaxy, just far away from matter, there's no gravity to deal with. And if this charge is far away, you just kind of give it a little nudge, and inertia will bring it to this location. You don't have to do any more work. So bringing that first charge is free. Now let's bring charge 2 in. But now charge 2 is going to have to interact with charge 1. And so to bring in charge 2, we have this interaction between Q1 and Q2. And then to bring in charge 3, where charge 3 is going to interact with charge 1, so we're going to have this term KEQ1 Q3 divided by R13. So that's charge 3 interacting with charge 1. It's also going to be interacting with charge 2 because charge 2 is already there. So to bring in charge 3, it's going to have to interact with that one as well. And so the total energy to build up this charge configuration, let's just write it all out. And that's it. That's the energy that is stored in this configuration. And you can see like each pair of charges, like Q1 is interacting with Q2 and it's interacting with Q3. You know, we've got like 3 pairs of particles here. And so I'm not going to write this one out, but imagine we brought in charge 4 and placed that somewhere. To add to this, we already have this built up, so if we brought in another particle, Q4, we would have to add 3 more terms. We'd have an interaction between, I'll just write out the interactions for charge 4. We'd have like U14, U24, and U34. And so there'd be 3 additional charge. And now we have 4 charges there, so if we brought in charge 5, then we'd have 4 additional terms. So by building up this charge configuration, we can quickly, we go from 3 to 6 to bring in the 4th charge. And now that there's 4 charges, if we brought in another one, we'd have to add 4, so we'd have 10 terms. And then 15, builds up pretty quickly. But like every pair of interaction, like charge 1 interaction, like charge 4, it's going to interact with all the charges that were brought up previously. And so like each of, it's like, let's just look at U24. Let's just write 1 down. This would be KE Q2 Q4 over R24. So each of these terms, basically you have this product of the 2 charges that are interacting divided by the distance between them. And so again, you have to you could write this as like a summation. Let's do that. Just like a general result. But our basic term, like every term we have, we're going to have this KE so actually this is going to be kind of a complicated thing to write. Let's see. Just using this summation notation, it might make it a little complicated. I think we have to have a double sum here where, it's probably not worth actually writing down. It's better to just understand the concept. But I said I'd write it down, so I should probably at least try. So let's say we have I is going to go, so we have n total particles. Let's start with that. So I think let's sum from like I from 1 to like n minus 1. And then for each one of those, J is going to go from so, I want to be a little careful about saying this, we'd have to check this result. But let's just see if that gets us the result for 3 particles. So in this case, we'd have sigma I equals 1 to 2. And again, we have I equals 1 to 2. And then, I don't think I wrote this right because I'm missing the interaction between 1 and 3. Let's see. So we start with, like, say, I equals 1. Actually, then it should be from Let me see if I get this right. So let's just try this for the case n equals 3. So if n is 3, then I would go from 1 to 2, and j would go from 2 to 3. And then we've got this. Okay, so in this case we have, we'd start with the inner one. So we'd have, let's just write down the term. We'd have j equals 2. So for I equals 1, we'd have j equals 2 and j equals 3. And then I goes to 2, and then we'd have j equals, yeah, we have to leave this one I plus 1 because I is changing. So yeah, if I equals 2, then j would just equal 3. So yeah, I think this formula works. So we'd have like I1, 2, I1, 3, I2, 3. Let's say we put in n equals 4 just to check. So if n equals 4, we'd have I go from 1 to 4, or 1 to 3. And then j would go from, well, I plus 1 to 4. So in that case, for I equals 1, we'd have j would be 2, 3, and 4. And then I goes to 2. J would be 3 and 4. And then I equals 3, and j would just be 4. So what we'd get is we'd have I1, 2, we'd have this interaction, we'd have this 1, 2 term, 1, 3, and 1, 4. So we'd have 1, 2, 1, 3, and 1, 4. And then here we'd have 2, 3, and 2, 4. So that's 2, 3, that's 2, 4. And then this interaction between 3 and 4. So yeah, that actually, this formula actually works. I kind of regretted writing it down because you're never going to use something like that. You just know the procedure. So you just keep extending this formula as far as you need it. So, yeah, forget that formula. Sorry, wrong button. But anyways, that's the idea behind this, the energy stored in the system. And we actually say that the energy is stored in the electric fields themselves. So like these charges they create electric fields around them. And we say that that energy is stored in the electric fields. It does not belong to any of the individual particles. Okay, so shorter video, but just kind of a topic by itself. And yeah, I'm going to stop this one here because we're going to move on to an entirely new concept, and that is electric potential. So that'll be a separate video.